This is a presentation on question 3, molecular orbitals by Harrison Annette. Question A. This is the molecular orbital diagram for oxygen, fluorine and neon. The antibonding orbitals have higher energy levels than bonding orbitals. This is why the antibonding orbitals are higher than the bonding orbitals. Starting from the lowest energy levels and then increasing upwards, the 2s subshell contains the 2 sigma G bonding orbital and 2 sigma U antibonding orbital. For the 2p subshell, there is the 3 sigma G bonding orbital, the 1 pi U bonding orbitals, the 1 pi G antibonding orbitals, and then the 3 sigma U antibonding orbital. The molecular orbital diagram for boron, carbon and nitrogen is mostly the same as the one for oxygen, fluorine and neon. However, in the 2p subshell, the 1 pi U bonding orbitals and the 3 sigma G bonding orbital have switched places. G stands for gerade, which is German for even, and U stands for ungerade, which is German for odd. The swap between the 1 pi U bonding orbitals and the 3 sigma G bonding orbital is due to mixing. Mixing is when molecular orbitals formed from the hybridization of 2s and 2p subshells have close enough energy levels to further interact. This can change the expected order of the molecular orbitals. Here, the 2 sigma G bonding orbital and 3 sigma G bonding orbital have interacted as they have the same symmetry. The 3 sigma G bonding orbital has increased in energy levels. However, the 2 sigma G bonding orbital has had a decrease in energy levels. There are no changes in terms of order on the molecular orbital diagram due to this decrease in energy. However, the increased energy of the 3 sigma G bonding orbital has meant that it is now in a higher position than the 1 pi U bonding orbital, which means the 3 sigma G bonding orbital has more energy than the 1 pi U bonding orbital. In question B, the original diatomic molecule is drawn out first, and then another diagram is drawn to show the changes in bond order and molecular orbitals. For O2, the electron configuration is 2s2, 2p4. This means the 2 sigma G bonding orbital, the 2 sigma U antibonding orbital, the 3 sigma G bonding orbital, and the 1 pi U bonding orbitals are completely filled. The 1 pi G antibonding orbitals are both partially filled. The formula for bond order is the number of the electrons in the bonding orbitals minus the number of the electrons in the antibonding orbitals, all over 2. And the bond order for O2 is 2 sigma G 2, 2 sigma U star 2, 3 sigma G 2, 1 pi U 4, 1 pi G star 2. There are 8 electrons in the bonding orbitals and 4 electrons in the antibonding orbitals. So this is 8 minus 4 all over 2, and this gives a bond order of 2. For O2 minus, alternatively known as superoxide, the electron configuration is 2s2, 2p5. This added electron goes into one of the 1 pi G antibonding orbitals to completely fill one of them and leave the other one partially filled. This changes the bond order to 2 sigma G2, 2 sigma U star 2, 3 sigma G2, 1 pi U 4, 1 pi g star 3. So it's 8 minus 5 all over 2. This gives a bond order of 1.5. This is a decrease this is a decrease of the bond order from O2, weakening the bond. For carbon, the same procedure is repeated. The original diatomic molecule is drawn out first, and then another diagram is drawn out to show the changes in the bond order and the molecular orbitals. For C2, the electron configuration is 2s2, 2p2. This means the 2 sigma G bonding orbital, the 2 sigma U anti-bonding orbital, and both the 1 pi U bonding orbitals are completely filled. The 3 sigma G bonding orbital is completely empty. This means the bond order is 2 sigma G 2, 2 sigma U star 2, 1 pi U 4. So 6 minus 2 all over 2. This is because there are 6 electrons in the bonding orbitals and 2 in the anti-bonding orbitals. So this gives a bond order of 2. For C2-, the electron configuration is 2s2, 2p3. This added electron goes into the 3 sigma G bonding orbital to partially fill it. This changes the bond order to 2 sigma G 2, 2 sigma U star 2, 1 pi U 4, 3 sigma G 1. So that's 7 minus 1 all over 2. This gives a bond order of 2.5. This is an increase from the bond order of C2, which will strengthen the bond. The difference between this and O2 is that for O2, when an extra electron is added, it goes into an anti-bonding pair, which will decrease the bond order and weaken the bond. Whereas in C2, when an electron is added, it goes into a bonding orbital, which will increase the bond order, and that will strengthen the bond. Question C wants a molecular orbital diagram drawn for NO+. The figures given show how much energy would be needed to remove that electron. The 2s is higher than 2p because it is closer to the nucleus, and so there is more attraction to keep the electrons in, much like how ionization energy works. The lower the energy needed to remove the electron, the closer the subshell is to the free electron line at the top of the diagram shown. The electron configuration for N is 2s2, 2p3. So for N+, when you lose an electron, that will be 2s2, 2p2. The electron configuration for O is 2s2, 2p4. The energy of the electron pair in the 2s subshell of O is too high for that of the 2s subshell of N to bond with it, so it forms a non-bonding pair. This is shown by the 3 sigma bonding orbital in the middle in green. And with the 4 sigma bonding orbital, both the 1 pi bonding orbitals and the 5 sigma anti-bonding orbitals are completely filled. So this makes the bond order 4 sigma 2, 1 pi 2, 5 sigma star 2. So this is 8 electrons in the bonding orbital minus 2 electrons in the anti-bonding orbital. So this is 6. It's all over 2. That will equal 3. And so the bond order is 3.